Welcome back, everyone. I hope you've had a great break and made use of the time to visit this afternoon's Operational and Technology Developments Forum builds nicely on the data forum that we've had before lunch. And it comprises 5 case studies on a range of topics, from leveraging demographic data to support leakage management, to digital twinning, utilizing real-time data and transformation outcomes towards calming networks. So a really rich and diverse afternoon. So please, again, put your questions in the session's chat area on the right-hand side of the screen, and we'll cover as many of them as we can. If there are questions we don't have time for, please meet up afterwards with the speakers in sessions in the coffee shop after each of the presentations. So our first presentation is from Scottish Water and from CACI. Welcome to Gina Bryden, Managing Consultant at CACI, to Martin Walton, Asset Planner at Scottish Water, and to Scott Young, Customer Services Operations Team Manager at Scottish Water. So they're going to take us through utilising demographic data to support leakage management.
Good afternoon. Hopefully you can see my slides,
Gina.
Pauline. Fantastic. So good afternoon, everybody. Thank you for joining us today. As Pauline mentioned, my name is Gina, and I'm joined by Scott Young and Martin Walton from Scottish Water to talk to you all about using demographic data to understand consumption and leakage. So as you can see, I'll kick us off at the beginning and to give you some context about Acorn, and then I'm going to pass you over to Scottish in action. First off, hopefully you all know who is CACI? Well, our work within water can be placed into 5 broad buckets. Everything we do is to enable amazing things with data, whether that is supporting with data and models, as we'll talk about here, or ensuring excellent customer experience, which will in turn enable you to achieve your PR19 or 24 objectives. Today, however, we're just going to focus on insight, and specifically around the postcode level Acorn. So Scottish Water will be referring to Acorn a lot within their models and the following slides. Acorn stands for a classification of residential neighbourhoods, and it segments postcodes into 5 categories, 17 groups and 59 types. We do this by analysing demographic data, social factors, as well as population and consumer behaviour. Scottish Water level, which are these categories here along the top, as you can see, with a 6th category for high rise. There are around 800 factors that describe these categories, and I've included just a couple of these descripting factors here. So as you can see, just by looking at things like house type and presence of children, there is already an impact on demand, with lavish lifestyles in larger detached homes, probably with gardens, and people like rising prosperity, more likely to be in flats with no children. Areas close to each other can also have very different demographic profiles. So these are 2 streets that are in Edinburgh. They're quite close to each other, but they look very different from a demographic perspective. So we have urban adversity, which is typically flats, and comfortable communities, which are typically homes in very close proximity. The pen portraits provide further insights with comfortable communities in larger homes, and urban adversity, typically in rented, that's normally mainly socially rented, but can sometimes be privately rented, but also in much smaller flats. So here you can see we have 4 major cities. So we have Glasgow, Edinburgh, Aberdeen, and Inverness. As you can see, there are clear, distinct pockets of the different types of people you can see within areas, as you can probably see in the neighbourhoods that you live in. Anecdotally, these maps also demonstrate as you'd expect. So Glasgow, as we know, is an industrial city. So we have clear pockets of affluence in the southwest of Glasgow, and that's typically the affluent living there to avoid the prevailing winds. And if any of you have been to Inverness before, you can see here that although we have big population within Inverness, the population on the outskirts of Inverness is of a much lower density, which you can see by the rolling farms, which is very beautiful up there in the Highlands. Obviously, the world has changed a lot with COVID, and really sorry to bring up COVID on this snowy day. But a really common question we have is, how can COVID behaviours be tracked using Acorn? as obviously consumer demand has changed so significantly with more people being at home. Well, we have mapped anonymized mobile app data to Acorn to track changes in movement. So at a national level, as you can see here, the population broadly follows government guidelines. So in lockdown V1, as I'm calling it, the movement substantially dropped down to 32% versus pre-COVID movement. You can see as the government restrictions, the population and at a national level has responded to each of them. At the moment, we're currently at around 54%, which has crept up during lockdown V3. That's likely because more people will be working now, whereas before in the first lockdown, a lot of those businesses were actually closed. What's really interesting is when we start reviewing the different demographic groups on a week-by-week comparison. So we've seen the categories, and the categories here reflect the colours. So you can see these are affluent achievers. We've got rising prosperity, comfortable communities, financially stretched, and urban adversity here. So this is 2 weeks ago. So you can see the less affluent moving around more. We've seen that throughout the whole of the pandemic, and that's typically because the people that are in groups like young hardship, difficult circumstances, they're not in jobs that enable them to work from home. So they're typically in work such as retail, carers, that sort of thing. But what we can see now from 2 weeks ago, which is really interesting, is we can start to see the older groups moving about more. So we have our mature money, our comfortable seniors, and also our poorer pensioners that are moving more than they were previously on a week-by-week basis. Now, that could be that they are out and about getting their vaccinations, which is fantastic news, but it could also be that they're starting to feel more confident in engaging with spaces again, and they can start to see that light at the end of the tunnel. So that's the background to Acorn. So I'm now going to pass you over to Martin to talk about the domestic consumption monitor. So Martin, over to you.
Thank you, Gina. So, yeah, thank you. Thanks, Pauline. Yeah, it was interesting listening to Pauline speak earlier this morning about the change going forward and actively working to reduce demand. Within Scottish Water, we've been reorganising under a transformation programme, and my role previously was in leakage strategy, and I'm now part of the economic demand management team. So I think that kind of gives a sense of where we're going with that. And we've also heard, you know, from Carol at Yorkshire talking about their smart metering programme and Affinity's use of AI and data science to understand leakage patterns. So I think we're very much, this presentation is very much in that space, and I'll go through this fairly quickly, but the this slide is just really explaining where we've come from. Back in about 2008, we set out to build a small area monitor. It comprises 130 zones with 10,000 properties. As Gina said, we've got the 6 different socio-economic groupings, and each zone belongs to a single homogeneous socio-economic group. And that's quite tricky, picking out a little bit of your network. You can see on the right-hand side, well, I've got a little graphic there, and it shows what we've done. We've basically isolated, you know, small areas of the network that the houses beyond the meter are all of a single Acorn grouping. So that took a bit of doing. And we also don't have any metered commercial properties in the zones. Now, we took some guidance when we set this up from Acquia. They had, just a few years before we set out on this, issued guidance, best practice guidance document on how to set up a PCC monitor. So we've more or less followed that to the letter. We've got ABB electromagnetic flow meters. We use Technolog and Halma loggers. These are now fast loggers that record at 15 and 1 minute intervals. Our consultant partners on this was RPS Group, who helped with the design, and clearly CACI are an instrumental part of this because it's around that differentiation of the socioeconomic groups in Scotland that we rely on to actually work out what the demand is in the country. Next slide, please. Okay. So moving on. Yeah, so we take the socioeconomic data, and we've mapped that to all the unique property reference numbers, all the address points in Scotland. And we've got the 6 groups there. You can see how it breaks down, affluent achievers at 20%, and so on. And that is pretty typical for what has been mapped out for the UK. I think the UK is 22.5% for that group for affluent achievers. And the Rise in Prosperity, to give you an example, is 9.3%. So we're broadly similar to the distribution of properties in Scotland as happens in the rest of the United Kingdom. Next slide, please. So yeah, as I said, we're measuring data, 15-minute interval on the screen here. We take pressure as well. We adjust the leakage using the pressure, working out an hour-day factor. And we also have not displayed it, but we record at 1-minute interval. Absolutely essential when you're doing this work to understand your night use, which is a component of domestic consumption. Next slide, please. So we have a big range, 130 sites, as I said, and you can see the scatter across the sites. Quite a lot of variation, but we bring all that together to a common point. And next slide, please. So we work out the PHC for each of the ACORN groups. You can see the sort of blue at the top of the graphic there, affluent achievers. These are the greatest consumers of water per household. They have large homes, 3 or 4, maybe 5 bedrooms, in fact, and high occupancy, high affluence. So it's things like high car ownership, large gardens that are driving that. And we work out a PHC for each of the groups. Next slide, please. So we have here, we have the ACORN group per household consumption for group 1. This is for April this year, and 511, you can see. So how we do it is we take that 19.8% of properties in Scotland belong in that group. So therefore, we do a weighting. So we take effectively 20% of that 511, which is 101.25 litres on the right-hand side. And we do that for each of the groups, and we end up with a monthly consumption figure for the whole of Scotland. Next slide, please. And we can look at that consumption profile for each day of the week. So we work that out. We see higher usage typically on a Saturday and a Sunday. Next slide, please. There we go. Yeah, so we can see here we've compared 2019-20 pre-COVID with what's been going on this year. And you can see the influence of the lockdown periods and the trends that Gina was explaining as we've all transitioned through this difficult year. But it's had a profound impact on our consumption patterns. Absolutely clear here that we've had a significant increase in domestic consumption month on month. And I can share with you, it's not in the graphic, but just last week we reported the January figure, and that was exceptionally high. That was up at just under 400 litres of property per day, which is exceptional for this time of the year. Next slide, please. So not only we're working it out on for the whole country as a monthly figure, we can break that down across the country. So we have the ability to report domestic consumption at every level of our hydraulic structure. So we can go from the highest level being Scotland. We work that right through to water operational areas, supply zones, down to DMAs, and that gets fed into our monthly water balances for managing leakage. Next slide, Gina, please. This is where it gets pretty interesting, really. A lot of maybe what's gone before most companies would be doing. But what we've done at the start of COVID, we wanted to understand the change in behaviors and how that was impacting our consumption profiles. So here we've got the diurnal flow for all of the ACON groups measured across April. So this is an average day in April for each of the groups. And I think, again, you can see quite clearly that the group that's driving that consumption profile with the highest consumption is affluent achievers. Next slide, please. Now we can use this to build some interesting demand models. So this is an analysis of a demand in Swanston DMA. It's a large DMA on the southeast of Edinburgh. So in April 2019, that was the typical flow that we saw then and recorded then. Next, please. And that the blue line is the flow through the DMA meter. So you can see here that we've got an excellent correlation using 130 zones that we have in Scotland. And now we've worked out with the flow profile for a demand in Swanston, where we don't have a PHC meter, and we've profiled what that would look like, and then we've compared that to the actual flow through the meter. Next, please. So moving on, here we are at the outbreak of COVID. You can see quite clearly that there's been a shift in demand and how we use water. What we've picked up in Scotland is that the night use is higher. You can see that the yellow line has risen slightly, so people are staying up later. So our night use is higher. We measure that between 2 o'clock and 4 o'clock, but we've picked up a clear increase there. People go to bed late, but they also get up late. And as you can see, we've got this shift about an hour and a half in the peak demand. But also people are in their homes longer during the day, and it's evident there that there's a lot more demand during that period. But then getting on for about 7 o'clock, things begin to normalize just after that, and we're back to pre-COVID levels of consumption during that period. But clearly there's a big impact on how much water is getting used during the day. There's some interesting peaks there that we pick out. You can see there's some little nuances that are very well replicated in the model that we actually pick up on the meter, particularly around that 9 o'clock event where people 9:30 are beginning to think about bed for children, and there's extra toilets getting flushed and teeth getting brushed and things. So we pick that up. Next, please. And again, this is what we've measured through the DMA meter for Swanston. The correlation factor here, I think the R squared was about 0.995. So this is very exciting. We've got a method of modeling demand for any DMA using our monitor, and we're getting very encouraging comparisons for the same for a DMA where we've got a meter. Next, please. So what I'm going to do is pass over to Scott Young, and Scott is going to explain how he, as an operational manager, is able to use intelligence and to tackle some of the problems that he faces on a day-to-day basis.
Okay, thanks, Martin. Hopefully you can all hear me. I apologise for not being on video, but some IT issues this morning. So Martin was relating to Swanston, and we've done that last year, and we've done it for a lot of DMAs when we were looking at the PHC model, calibrated monthly average against the monthly average of the zone, the DMA. Swanston correlates really well, and that's because it's predominantly domestic. Very high percentage, about 98+% domestic properties with very little non-domestic influence. And we were starting to notice that the the flow had changed by about 60 to 90 minutes in the morning, so the peak draw was starting a bit later, but it was also higher. And on average, we're seeing about 15 to 20% increase just at the COVID time. That started to send the operational alarm bells around our pressure management. So along with Utilitech, our pressure management consultant, we started to look at where we had possibly time profile issues on PRVs, where they might now experience customer low pressures due to the shift in demand. And we were also worried that we do get some nice weather in Scotland now and again, but we were also worried if the summer hit us, what that increase would do, because typically we see a 15 to 20% increase in domestic demand during the summertime. So that would have equated to a shift in the morning draw, but a peak that could be significantly higher, 30, 35%. So we started to run the PHC model calibrated, where we knew the percentage of domestic was high and the likelihood of this would happen. We've done that over 1,100 PRVs, and we've seen a direct correlation. We also used the data that we had into a hydraulic model, so we started to work out the pressures within the inlet to the PRV and externally to the PRV, and we worked with some of our framework suppliers to look at the characteristics of the PRV, and we started to be able to calculate where the stem position would be inside the PRV, and therefore where it would be up at its upper range and possibly become unstable. So that put a watching brief of some 1,100 valves over the summer period that Utilitech were monitoring for signs of change and signs of demand-related pressure drops. We managed to get through that event successfully, didn't generate a lot of low pressure customer complaints, but we also started to see other trends, and there's some examples of some of the things that we've started to use this calibrated model for. Next slide, Gina. So we started to look at in relation to our leakage. Sorry, I don't know if you could go back one, Gina. So where we started to look at the PHC model. So again, we were looking at the tipping point of when the non-domestic percentage is high. We do get a wee bit a difference in the model, but in this instance here, 82% domestic, about 8 litres a second, 0.8 litres a second, sorry, for our non-domestic usage. And we can actually see that the curve's quite consistent based on a 30-day average on the PHC and the zone. It's about a 2,000 plus DMA. And we were quite comfortable that we're looking for leakage. So you've got your average actual flow going into the zone, your average PHC flow, and then we've created this band of minimum night flow, typical leakage calculations. But we can actually say that at this point, we think it's not demand-driven, particularly tough DMA, all plastic, and we had a concentrated effort using new techniques in digital mapping. Next slide, Gina. And the result is we achieved the leakage reduction through having that consistently and having a focused attention that we knew we were going after the right thing. And we've pulled the night line down to where we want to be. Next slide. Other things that we started to notice was where you've got in this graph, another DMA, it does supposed to be quite high, non-domestic, around about 96%, with only about 20 to 30 non-commercial commercial users in there. But what we started to see on the left-hand side at the night time when we were measuring leakage, we actually see the graph flattening on the actual average flows compared to what the PHC model was telling us that it should be still going down. So we turned the loggers on to 5-minute average, and we looked at the minimum flow in that 5-minute period. So we looked at pulse interval timing, we looked at the low flows, and we actually found that there's a user in there that's using about 1.4 litres a second on the average 30-day analysis. We need to get around there into these properties. Obviously, restrictions at the moment are around COVID, where we can't do the usual internal inspections. But what we're really saying there is we shouldn't do leakage. We really need to find that unaccounted for water. Next slide. And this one through a bit of confusion. So this is another DMA in between Edinburgh and Glasgow, typical small town DMA. But what we were actually seeing was the PHC flow in peak demand was actually higher than the average actual flow. And we've seen that consistently on a 30-day profile. So we drew the conclusion that this DMA is not tight. It has a passing boundary valve somewhere. Again, we spoke with our hydraulic modelers. We used these average PXC flow graphs to put into the hydraulic model, and we're quite comfortable that we've calculated where the valves are that are passing. There's two strongly suspect valves. One's now booked to be dug up. It's on a busy junction typically, but it's due to be dug up, and then we will find out if that's passing or not. We've calculated that to be in the region of about 0.9 to 1 litres a second as it transfers through, and we suspect that we've also at night got the water leaving the DMA from somewhere else, possibly in the trunk main. So again, still under investigation, but the model highlights these kind of things. And if you go to the last slide, we also see that it started us to think that could we lose a model for building up curves for pressure management, especially from an economic demand management that Martin mentioned. So this is a small DMA, 100% domestic. It's only about 200 plus properties, mostly single services. Nice tight DMA, no real leakage, but in this grey section, which is where we're typically managing pressure, 2 to 4 on a very simple time profile, we see the actual flow for the DMA go below the PHC demand profile. Now, we're thinking that is driven from a 26 to 27 metres head at 2 to 4, where our average PHC models, the 130 odd zones that Martin mentions, are typically at 40 metres head and just below. So we're thinking that we are actually controlling some of the water loss through the pressure management at that point, as we would do for normal leakage. And it started a conversation with some of our service suppliers around, could we use these PHC curves to really micromanage demand and actually challenge ourselves to get the average daily demand profile below our PHC, and use that as a measure to see if we've been successful with micromanaging the customer's tap and the ability for them to draw water. Next slide. So we're comfortable going forward. We've got high confidence now in the Acorn PHC model, and we're ensuring the right resources are in the right place. So we're quite comfortable that we can identify leakage and where we need a concentrated effort, and where we can look for unaccounted for water. It highlights it in the PHC model. And we're hoping that we can ability to optimize the water supply using this model, linked to hydraulic models, linked to the small monitor model, and we can really build up quite challenging curves to manage customer demand. And we think we're going to use this for looking at measuring the efficiency of any intervention we do in campaigns for the customer to be more water efficient and reduce consumption. And that is us. Thank you.
Thank you very much, Scott. In the interest of time, I have one question, which hopefully one of you can answer in 2 minutes. Do domestic consumption models challenge the need
for answer that, Martin?
I'll start off. Well, I mean, in Scotland, there is no intention to bring in compulsory metering, and people don't seem to want that. However, anyone in Scotland can apply for a meter, and Scottish Water will very much support an applicant in that if they believe that the person would be able to save some water and become more efficient. Then we'll give them every assistance with that. Despite that being on the table, there are only some 300 plus properties in Scotland with a domestic meter out of the 2.5 million. So Scotland is really, you could say, is all unmeasured, really. Where if we were to go down the metering route, just taking rough numbers, it costs about £1 billion to put the meters into Scotland.
Yep. And
then we've got some to to kind of read these and manage that estate. So I think where we see it being better directed, that money or some of the money that we might have for an investment is into non-domestic metering. and we'd like to bring in more smart metering in that area. And we think that could be quite beneficial to complement the model that we have developed with CACI. And we envisage in building, perhaps together, hopefully, another model that will give us the same abilities around the non-domestic monitor. That's an intention.
No,
Scott, would you like to add quickly anything onto that?
We're trying to understand where the tipping point is and find out where the real benefit would be from non-domestic metering when we add it to that PHC model and the data that we've built up over the years. So that's, as Martin says, is probably the next place or where we would like to go, is looking at that.
Okay. One more question. How do your rateable values or equivalent map to your Acorn categories? That's from Lewis Budworth.
Okay, well,
1 minute.
It's not something really we looked at. When we set out to do the stratification, we looked at the options that were recommended in the best practice, and one of them was looking at things like rateable values, looking at the council tax bands and using that. But for different reasons, and the way that the different local authorities apply their assessments, the rateable values are assessed differently in different local authorities, and council tax bands are assessed differently in each local authority. So we went with the CACI Acorn methodology as being a consistent method of stratification. So we haven't looked at it in detail, but when we did touch on it, it didn't look robust enough to do the modelling that we're now doing.
Okay, I think we're going to have to close this group of presentations here. Thank you very much to Martin, Gina, and to Scott. Really good food for thought. And now I'm going to introduce the next presentation. And so as you exit, I will start introducing the next one. So next one is IDMA, tapping into near real-time data. And presenting for this session is Robin Corby, Commercial Sales Manager at Technolog, Daniel Woodworth, Network Strategy Manager, SCS Water, Tom Woolley, Business Development Director, RHD HV. So Daniel and the team are going to provide insights into delivering a company-wide intelligence network in AMP7 and how that is going to reduce leak runtime, increase operational efficiency, improve customer efficiency, and reduce environmental impact.
Okay, thank you, Pauline. Hopefully you can hear me okay and see my slides. Can I just do a check on that? Great. Lovely, thank you. Okay, well, thank you for having us here to present. Yes, so we're going to be talking to you about SCS Water's Intelligent Network project, which we're calling the IDMA project. So delighted to be joined today by two partners on this project. So Robin Corby from Technolog and Tom Woolley from Royal Haskell-Union DHV. I think the fact that the three of us are speaking today really shows what a collaborative project this is. And how we really see collaboration as helping to deliver this for us. Okay, so I thought I'd start just by introducing sort of some of the aims of the project, and hopefully you can test this as we go through the presentation. And I've got a case study at the end, and I'd like you to kind of think back to these aims to see if you feel we've met what we set out to do. So what we're trying to do here is get a reliable and consistent near real-time data from our network. And with that, we'll be getting real-time alerts with high confidence levels on those alerts so that we can act on them and make the best decisions. So it's all about putting our knowledge at the fingertips of our operational staff so they can react quickly, make the right decisions on site. And it's about having that information-backed decision-making. So not being put on the back foot, but rather being on the front foot for that. You know, we're looking at improved location and detection times. So you heard Jeremy Heath earlier talking about the palm analogy. So this is very much in the field of location and detection and reducing that part of the leakage life cycle. And if we can do that, we can reduce the runtime of the leak and the impact and the volume that it therefore has on our network, on our customers. And we want to improve our leakage position. Obviously, that's one of the main aims, but there are many other benefits as well. So this will have a positive impact on supply interruptions and on burst main performance as well as other performance commitments such as customer service measures as well. And that brings me on to the customer service element. So really what we're aiming to do here is know about network events and issues before our customers do. Again, it comes back to that point about putting us on the front foot. We in our business, we often talk about the golden hour concept. And so, if we can act in that golden hour, you have a lot more options than you do if you let things run on for longer. Approved information to update and advise the customers. So when things do go wrong, and sometimes they do, the customer will call in and want answers. If we've got the data to back us up, we can answer those questions much more easily and with the best information. And we want to reduce the impact through the runtime. So again, we accept that occasionally the network will fail, but we want to minimize the disruption that's caused by that failure. And earlier identification. So, the aim is to get there, solve the problem before the customer's even noticed. So as I've said, we aim to deliver this all through a collaborative approach, and that's working with our key partners on this project. So just to share with you what our vision for an intelligent network is, and this is a slide that I've been using for quite a while now, but I want to make the point that this isn't one size fits all. So what we found, even within our relatively modest stock of DMAs that we manage at SES Water, you need a variety of sensors, a variety of different attributes that you're measuring, but you need a common way of getting that data and that information back, and then ideally a common method for processing that data and producing insights from it. And that's what we're aiming for here with our vision of an intelligent network. I call this a vision. It's not really a vision anymore. We're actually up and running now. We've got near real-time data coming in within in all of our DMAs now, and we are on the cusp of having the AI engine running on that Tom will talk to you about, running in all of the DMAs as well. So this really is becoming a reality across the entirety of our network now. And we identified quite early on that there were building blocks and stages on this journey that we needed to go through. And this is, really where we decided that we needed to team up with the right people. So, we've got sensors, and Robin will speak to you in a minute about what Technolog bring to this project. You've got the communication piece. We're using the Vodafone NB-IoT network for that. And the processing layer is what Tom will speak to you about, the RDA, Royal Haskoning are bringing as well. So I'll pass over now to Robin, who's going to take you through the first of those building blocks.
Thanks very much, Daniel. And just similar to you, can I just check that everyone could hear me okay? Just a thumbs up. Okay, yeah, as Daniel mentioned, we wanted to
we can
provide near real-time data, and to do that we have to provide the two building blocks that you just showed you in terms of enhanced communication and enhanced sensors. And one of the ways of having that with the enhanced communication is enhanced technology in that field. And a key element around the characteristics of NB-IoT lends itself greatly to the characteristics of our loggers that have been deployed. To date, there's over 600 loggers deployed in SES Water with this technology. And I've given you a snapshot of where they are, and I don't expect anyone to go out in a Pokemon Go style looking for these loggers out there in the Sutton region. But there's a high density of logger deployment that's out there. And these are largely deployed underground, so the signal needs to be have the best opportunity for the data to be transmitted through the remote communications technology. And NB-IoT lends itself very well to that because it works on lower frequencies, lower bandwidth, and it gives that extra ability to penetrate the likes of lid covers or buildings to get to our devices, so it could reliably transmit that data as and when we need them. as I mentioned, also, it's quite a high density of deployment out there. So when you have the infrastructure, you want infrastructure that's available, and to reach a large range, a long range of where these loggers are deployed remotely. So when you have certain masts with the infrastructure in place and you have several loggers, this gives you a great opportunity in terms of getting the penetration and the distance of the signal as far to the end of your catchment. Similar to that, because I mentioned earlier, the low bandwidth that operates in NB-IoT enables the device to run at lower power requirements. So they allow the hardware, the cellular hardware, to run at a lower power than it did in the kind of 2G world. So that allows the device to last longer if it's using that particular technology. And it also lends itself to the type of communications that are typically transmitted, which are frequent communications with small packets, which I'm going to demonstrate here. We'll go on to the next slide. Thanks very much. So, what do you need for enhanced data? So it needs to be near real time. It has to be reliable and consistent, and to provide additional sensor metrics, so some more information about your network. And we've have a long history of working with SES Water, and I wanted to show with this slide that we've got, in some cases, up to 10 years worth of data, reliable data. And traditionally, as you can see from the line in the graph, that's typically been flow and pressure data. So two channels of data that's been transmitted every hour, so 60 minutes. So we've got a lot of data that's available, but moving into the new world of the IDMA, you have to provide more information about your network and provide that consistently without having a detrimental effect in terms of the operation of the device and the length of time that it could, the life cycle of the asset within the ground. So as of the installation, we're able to move from having 2 channels data to 8 channels. And I'm selling it short a little bit because one of those channels is a statistical channel which provides the maximum, minimum, mean, and standard deviation of pressure, and will help with things that Scott Taylor was talking about in the previous presentation in terms of detecting PRB instability. So, and also providing other new metrics that are being looked at more in terms of temperature of not just the ambient temperature, so the environmental temperature, but the temperature of the network as well, and how that change in temperature manifests itself in terms of bursts and events within the network. And this data now is being transmitted every 15 minutes and has to work seamlessly with the AppSuite software to provide that data and as and when it needs it to run. So if we go on to the next slide, Daniel. So the key part of all of this, as we mentioned probably several times throughout the day and also within this presentation, is the collaboration, that element. So we need to work together to make sure that all parts can provide what they need to do. So one of the key priorities for me was to ensure that SES systems had the consistent data that they always had, and those links are maintained, but also add to their capabilities by adding additional channel data to the existing systems and the new systems that are being developed and implemented. So that means working with AppSuite and SES Water to come up with a consistent way of collecting that data and a consistent and robust way of transmitting that data to their systems and to the right systems on time. And all of these systems run pretty much like clockwork, so the data has to be there and available for them to do that. If that falls apart, then the next part cannot be maintained. So that's why I'd like to hand over to Tom so he could talk about how our data is being used with the AppSuite system.
Thanks, Robin. And just check everybody can hear me okay as well. Great, thank you.
Yes,
so
we can, yeah.
Robin and Daniel have really set the scene in terms of the data that we need for AppSuite. And key to what Robin mentioned in the previous slide is it's really important we get that data reliably and consistently and in a timely fashion. Because what we're trying to do is to provide, I suppose, two outputs for the project. The first one being detection of leaks. So we enable Daniel's team to be able to see when a leak has happened in real time. So we want to take that data in from the Cello data loggers provided by Robin and Technolog, analyze it, do the machine learning detection, and then tell Daniel's team whether he has a problem in his DMA and whether he needs to get his crews out there to look at that. And that all needs to happen really quickly. So just as Robin was saying, we need to get that data through every 15 minutes because our analysis doesn't just depend on the single instrument. We're looking at the whole DMA as a system. So we need to get the pressure data from the critical point, we need to get the flow data from the DMA, and use all that data together to detect any deviations and hence any leaks. What we're doing is importing that data from the sensors. We use our machine learning algorithms, which we've developed over the last 20 years, I would say, to predict what the pressure and flow should be at that particular moment. Now, I'm not sure how well the image is coming through for everybody else. It's a little bit blurred for me on the screen, but hopefully on that middle trend, the top trend there, you can see there is a blue line and a green line. And on the left-hand side, those lines are going along close together really, really nicely. And this is genuine data from one of the DMAs within SCS Water. That's the predicted versus actual. So the green is the prediction, the red is the actual data, and then the blue line is the machine alert alarm limit. So what we're doing is we're looking to see that the red and the green are really close together, and if there is a deviation of the measured data away from the prediction, it then goes past that alarm limit and we raise a leak alarm for Daniel's team. And that's what you can hopefully see in the middle of that trend there. So the green and the red go along really nicely, and the red zooms up past the blue line and we raise an alarm. And that's the first part of the solution. So at that point there, as soon as that change has happened, in this case, because it's quite a big change, we raise the alarm and Daniel's team now know there is a leak occurring at that particular point. Most leaks don't tend to start appearing like this one here. So they tend to start with a smaller flow amount, and that might not be instantaneously visible as it would be in this trend here. So the one on the bottom, which I suspect isn't very clear for anybody, is actually looking at the effect of smaller deviations over longer time periods. Because a small leak, if you look at it in 1 minute or 15-minute samples, is very small. But if you look at that smaller leak volume over 1 hour, 2 hours, 3 hours, 4 hours, it becomes more apparent. And the AI is able to predict not only what's happening now, but also what's going to happen for the next hour, next day, next 72 hours. And all of that together can then start to pick up these small leaks, which eventually will become bigger leaks. So the idea is to get instantaneous awareness of any medium or larger leaks, but also pick up the small ones by looking at the effect over longer time periods. If you go to the next slide, Daniel, if you don't mind. The second part of the solution is helping Daniel's team to find leaks quicker. So the first thing is we've told the leak teams you've got a leak, and we can estimate the size of that leak as well, because the deviation away from the prediction of the measured data gives you an estimation of the leak flow. And that's fairly accurate usually. So we've got an estimation of the leak flow. What we then need is a DMA which has got multiple pressure sensors. So in the past, that would have been unrealistic because I think the technology wasn't available and it might have been cost prohibitive as well. But as we move to this era now where we've got IoT sensors, NB-IoT and other solutions, we can get to the point where you can have a DMA with maybe 4, 5, 6, 7, 8 pressure sensors within it. I mean, most DMAs already have 2. You'll have a DMA flow meter, which has got a pressure, and you'll have a critical point. So if you're looking at adding another 3 or 4 sensors, we can then use that leak flow estimate and that pressure data to locate where that leak might be. So the solution's got 2 benefits for Daniel. The first one is to tell him when a leak happens really quickly. So we're not waiting for a nightline analysis. We're just raising that as soon as it happens. And the second part is to enable his leak localization crews to go to a particular part of the DMA rather than look at the DMA in a whole. And obviously, in the age of leak crews becoming more and more scarce or more costly, being able to prioritize where they go to without saying go and look at the whole DMA. If we can just say go and look at that 20% or that 10%, then there's real benefits there in terms of efficiency, but also for the customer, because you can enable that leak to be found, repaired, and get people back on service much quicker as well. So we take the estimate of the leak flow. We then model the effect of that leak flow on the nodes throughout that DMA. So if you look at the DMA, in this one in particular, it's quite a small one. We model the effect of that leak flow on every node, and we calculate the likelihood of that node being the leak localization, sorry, the leak location point, by comparison with the actual pressure data. So again, it comes back to the fact we need that data reliably, because we're simulating, comparing simulated pressures with actual pressures in real time. And this all happens as and when the data comes through. That's why it's really key for us to get that 15-minute or even 30-minute data through reliably, consistently, and with really good date and timestamps. And we can then get to what we can see on the next slide, Daniel, if you don't mind. And this is the results when it comes up. It's quite a hefty image that might be difficult for people to see. This is the results of some actual tests we've done within a DMA, the first DMA in SCS water. So hopefully everyone can see towards the top of the page there's a gold star. So you can see the critical point. Hopefully just next to that there's a gold star. That was the location of the leak test. So there was a leak test performed there, which I think was around 1 litre a second. What we then did was set the burst find module going, looking for that leak. And the output of the burst find solution is likelihood of the node for being the leak location. And we represent that as colouring and size. So the bigger the dot and the darker the dot, the more likely it is for the leak location. In this case, you can see at the bottom left that you can see lots of small dots, green. At the top left, you can see lots of small dots, which are sort of amberish. But on the top right, you can see big red and black dots. And that shows that our solution detected that location as being where the leak is. So if this was a real leak, what would have happened is that burst alert would have detected the leak, burst find would have generated this simulation, and Daniel's crew would be able to look at this and say, right, it's really clear from this that we need to go and look for this leak at the top right-hand part of the DMA. And that's the big win. So we're not pinpointing the leak. I think that's challenging to do with pressure data alone. What we're doing is really shortening that time between the start of the leak and when the guys can get out there, pinpoint the leak and fix it. And if we go to the next slide, hopefully this image won't take quite as long to load. Here's a result of a second simulation, which is a similar size leak, which actually took place at the bottom of the screen there, the gold star. Hopefully you can see that. And we simulated this as well. So we've got, I think, only 7 pressure sensors in this DMA. We started the leak at that gold star. We ran burst find, and burst find quite clearly chose 3 nodes at the bottom of the screen as being the most likely location for the leak. So, and again, the actual leak was right in the middle of those other 2. So it gives a really good result. And the leak crew wouldn't need to go and look around that DMA. They could just go straight to that location. Additional techniques to then narrow it down to an exact point, and you can get out and fix it really quickly. And on the next slide, Daniel's going to talk through an example of how that might happen.
Okay, yeah, thank you, Tom. So conscious of time, but I just want to quickly show you how this works and the benefits that you would get from it. So this is a real example. This is a burst that we had on our system. And I'm going to do a bit of a before and after. We had the advantage of this being in one of the test areas that we set up. So we had the opportunity to kind of look at what would we if we'd have been running live with AquaSuite when we had this burst. So you can see, and I'll try and point to it here. So we had the outbreak of the leak. This leak, it wasn't visible. So the first we were made aware of it was the day after. It's when a customer called in with low pressure. And we did send, it was at the weekend, it was on a Sunday, so we did send one of our out of hours crew out to look for it, but it wasn't visible. And this is a long rural DMA. We've got mains running across fields, and they didn't have much luck. They weren't able to find that leak until I think it was, well, yeah, early on the Tuesday, when the leakage team went back for a second try and managed to locate the leak, and that's when the job was raised. There were then some engineering difficulties. The leak was in the middle of a field, and so it took a fair few days for that to actually be repaired. We had to get the landowner permission, etc. So the total runtime of that leak was 77 hours, 3 days, and we lost 1.9 megalitres of water as a result. But if we'd have had AquaSuite working and we'd have been using it as an operational tool, it was working, we were just it was just in shadow mode. Here's what we could have done. So we had the AquaSuite alarm come through, and that's just the screenshot there of what it looks like and the email that gets sent to the operative to act on. So here's what the graph could have looked like, and try to bear in mind what we're trying to do here is squeeze down the detection and location time. So these sections here. So you know, this is based on some assumptions, I will admit, but I think they're all reasonable. So the leak would have broken out at 14:30, the same time. The alert would have come in and would have been by 1800. We would have had that alert. We would have immediately dispatched an inspector to the area who would have had access to the burst find, which would have pinpointed or located that leak to the section of main that it was on. We then would have found it a lot quicker, and we would have raised the job around about midnight on that first day. I've left the repair time the same because, as I said, there were engineering difficulties in getting in there. But what you can see here is that by dramatically reducing the detection and location time, you can really bring down the volume of water that's lost. And because we know leaks increase over time, it's that golden hour thing of really getting in at the beginning of a leakage outbreak, and that's where you get all the benefits. We also wouldn't have had the customer contact on this one as well, so there's other benefits there as well. Or if we did have the customer contact, we could have told them that we knew about the leak and we were onto it and there was a repair raised. So hopefully that just gives you a bit of an idea of what we're trying to achieve. And that's it from us. Thank you.
Great, thank you, all of you. We have a couple of questions here, which again, keeping an eye on time, if you could keep the answers fairly short. First one from Mikael Wilmot, really interesting and very exciting presentation. Sometimes demand can appear as leakage when using live data. Does this make false positives more likely? And if so,
thanks, Mikael. Really good question. On the first slide that I showed, we've got the predicted versus actual in terms of prediction and measured data. We also have that machine learned alarm limit, and that's the key to filtering out demand and trying to prevent natural or normal demand being picked up as leakage. If your alarm limit takes into account how much that prediction normally varies from the measured data, because maybe your DMA is influenced by commercial usage, things like that, you'll naturally find that the band between the predicted and the alarm limit is a little bit bigger than what we saw in the image to start with. And in that case, you try and prevent normal demand being picked up as leaks. It's always going to happen, false positives, but I think we've done a lot of work to try and filter those out wherever possible. And we did develop this solution with 6 water utilities in the Netherlands, so we've got a lot of understanding of how to try and do that. But there's no simple solution, unfortunately, to say we'll never pick up a false positive, but we'll do our very best to prevent that.
Yeah, just to add to that, there is also some capability within the software to effectively link DMAs to each other. So this is to overcome, the sort of summer watering scenario whereby you know that neighbouring DMAs are going to react the same. And so if you see the behaviour happening in more than one DMA, the software is intelligent enough to alert you to that, or at least make you aware of it, and then not alarm on it.
One thing I sorry. Okay,
we have two more questions. If I can just quickly ask them, and again, some quick responses would be appreciated. Adam Smith asks, can you please elaborate on the advantage of using pressure sensors in addition to acoustic, I think acoustic loggers?
Thanks, Adam. The point I made at the beginning was that this isn't one size fits all, and so there most definitely is a place for acoustic noise loggers as well. I think we've decided to have a look at pressure, as a means of localization. But we know that there'll be some DMAs where acoustic works well as well. I mean, one of the things we'd like to do is continue this project and look at actually getting some of the acoustic data to build into the software as well, and almost act as a validation potentially, or get pressure acting as a validation for it. So get them working together, because it's just going to add to the certainty of where you're ultimately going to go and look for the leak and dig.
Great. And the last question is from David Jacobs. Have you tested if the solution is capable of picking up smaller leak volumes that are typically found on supply pipe leaks?
Tom, do you want to take this one?
Yeah, go on. So yeah, I was about to say to David, the bit of supply pipe leaks are challenging for everybody. I think it depends on the flow in the DMA itself. So your night line or your DMA flow is quite low. A supply pipe leak, not at an instantaneous point, so you won't pick it up on a 1 minute or 15-minute value. But if you look to the effect of that supply pipe over 15 minutes, over 4 hours or 12 hours, then yes, it might be possible. But it really does depend on what your background leakage is in the DMA.
Very good. Okay, we're going to have to close with that. Thank you very much, Daniel, Tom, and Robin. That's been a fascinating discussion. Again, as Judah has indicated, if anybody has any more questions, you can catch up with the guys, I think, over the expo. But now I need to move on to the next session. And joining us for our next presentation are Robin Bell, COO of Inflowmatics, and Jamie Jones, Leakage and Smart Networks Manager from Portsmouth Water. Robin and Jamie are going to look at how learnings from AMP6 and the pressures from COVID-19 and unprecedented demand led to a unique opportunity to take a proactive approach to addressing issues within their pressure-reducing
Good
valve
afternoon,
state.
everyone, and thank you for the opportunity to present today.
Robin and Jamie.
I'm delighted to have worked closely with Jamie over the last few months to really understand the challenges Portsmouth Water face and where our solutions can be applied. Jamie and I will now summarize the progress we've made working together in developing genuine outcomes with the ultimate goal of achieving calm networks and extending asset life. Firstly, for those of you who don't already know us, I'll give a very short introduction of Inflowmatics. Go to the next slide. Thank you. So Inflowmatics was founded in 2015, and over the last 5 years, using the intellectual property we've developed in conjunction with Imperial College, we've worked with a growing number of customers, particularly in the UK, worked with many of the people who are attending the conference today, but also worldwide to understand the problems we can really help solve. Our solutions have been widely developed, leading to significant business growth over the last few years. Now, our latest product offering is called Arboristi, which, again, in close collaboration with Portsmouth Water, has allowed us to demonstrate really tangible benefits. So I'll talk a little bit about Arboristi. So what is it? It's, in summary, a digital tool can only be as good as the accuracy of the input data, particularly when developing real-time models. It has to be good input data. Arboristi is truly sensor agnostic, but it does benefit from the highly accurate high-frequency pressure data we can provide from the Inflowmatics sensors, amongst other inputs, including flow. And what we can create is a calibrated live hydraulics-based model. From this model, we generate outcomes, which can be used directly in decision-making, particularly at an operational level, operational and strategic, in fact, which Jamie will talk a little bit more about later. And you'll see some very clear examples in the next few slides from Jamie. Our goal, of course, is to achieve calm networks and extend asset life. And when we talk about asset life, we're not actually just talking about pipes, although those are critical, but also all assets on water networks are impacted by non-calm networks, by transients, by those kind of effects. So I'll now hand over to Jamie to talk about the Portsmouth Water Network in more detail and the journey they're taking towards a digital twin.
Well, thank you, Robin. Pauline, can you hear me? Excellent. That's a good start.
Yes, I can.
Are complicated, and understanding what is really happening within them is very, very difficult. We have different pipe materials that leak and fail in different ways. We have parts that are pressure managed and other parts are boosted. Our customer demand can be erratic and change from day to day or from season to season. And new sites are added to the network often. Our networks basically are regularly changing beasts, and no 2 days are the same. So why do we only update our network models once every 5 years? The answer used to be that we could not afford the sensors. But now we have more sensors, flow, pressure, noise data than ever before. The answer also used to be that there's not enough signal on our network. In the world of IoT, that has massively improved our data communications. The answer also used to be that it was not needed in order to achieve our targets. With the 50% leakage by 2050 and the reducing interruption to supply challenges out there, it means that that is also no longer the case. Now we need to have faster and more informed responses to incidents than ever before. We need to get much better at targeting our main renewals and to prioritise our maintenance. We also need to save as much money as possible, and also, perhaps most importantly, stop causing a lot of our own issues on the network. Now is the time for us to take all of our data and put it to its best use, to create real-time calibrated and automatically updated network models, and to actually start understanding what is happening on our network. So of course, we've been working with informatics to explore what benefits a digital twin could actually bring. My first example is a PRV failure that was on our network. In this instance, Operacity was able to determine a potential issue and allowed us to send out a PRV technician before the PRV would fail. This early warning gave the technician time to resolve. It also gave our operations teams time to prepare for the worst. In an ideal world, the PRV would have been resolved and there would be no burst on the network and everyone can be stand down. The crisis averted thanks to the early warning. Unfortunately, in this scenario, the PRV did still fail before the technician can actually fix it. And it caused 3 bursts on our network. But our teams were ready and sprung into action immediately. The 3 bursts were found and fixed quickly with no interruptions to customers. The crisis was managed thanks to the early warning system. My second example is a digital twin. Benefits can come through network calming. In this example, a customer reports severe pressure fluctuations on the network, and we deploy informatics sensors who, through the clever CPS score, which is an algorithm that's kind of works out what stress is happening on the network. They managed to determine that our network in this area was under considerable stress. So ideally in a network, a CPS score should be no more than 500, and we had 90,000. We had transients every 6 minutes. We had major pressure changes on the network throughout the whole day. And something was obviously very, very wrong, even though it was below a PRV, a monitored area. So we worked together with informatics in order to identify a potential solution, and this did prove to calm the network. Unfortunately, this solution needed additional network infrastructure, and so therefore we had to plan that in, but we did, and it was installed, and it did lead to the network being calmed and a significant reduction in those pressure fluctuations that the customer was experiencing. Things were still not perfect at that point, and so we've continued since then to further identify issues on the network and continue to calm the network as much as possible. Through work that we have done and also other water companies have done, we estimate that the network calming that, if done over the whole of the ports of water network, will reduce our burst rate by 18%, and that is not to be sniffed at. Our third example here is a large user in Scotland that requested to take a large amount of water in one go over a week. We modelled this and set out a kind of flow profile based on our out-of-date model. The user started using, and informatics came in at this point and pointed out that the water being taken was having an effect on the network and was causing additional stress. They proposed a solution to fix that, which did drop down that CPS score, and then after the water was stopped being taken after a week, the network was calmer than it ever had been before. Unfortunately, in this instance, there was a burst a few days later, and what that does is it's really told us that we can't base any of our analysis based on out-of-date network models, and it's really very important to have the latest data. As said before in other presentations, it's very much a case of rubbish in, rubbish out, and very much a case of having great in and great out. A final example here was a load that happened on the network this summer. There was a massive increase in demand through COVID, and it happened in certain areas, and this is one of them, and we started to get some very low pressures on certain parts of our network. We went out and investigated and just made things worse, to be honest, and therefore over to informatics in order to try and investigate what was wrong. Our technicians have said that all valves were open, and we believed them. But Robin and his team did not, and they argued that there must have been a closed valve on a network. We double-checked this valve, and it turns out informatics were right. And so, taking Jez's palm analogy to the next level, hopefully, you can see that and the life of a leak. It's also taken from work from RPS as well, so I can't lay claim to any of this. But you can see there's the prevent, awareness, location, and mend time. And for us, I've identified kind of 4 areas now that I'm really keen to make big improvements in order to improve our leakage figure and reduce leakage as much as possible. And arboricity is certainly going to help us with calm networks and prolonging the time before a leak occurs. And also you can see how it also will work in the future for automated identification of leaks and location of leaks, similar to what Tom and Daniel proposed in the last presentation. And so to the actual tangible benefits. I've mentioned the 18% reduction on bursts, but we've also estimated a 12% reduction on repair costs and a 23% reduction on detection costs. That means we are able to stay at our current level of leakage detection and repair going forward whilst reducing leakage. We've also started to looking at other benefits such as operational and strategic benefits. We've seen a huge benefit to operations, of course, as we explained in here, but also into that long-term planning. And again, it very much comes back to the rubbish in, rubbish out, and through having far more accurate data being put into our models and into our planning to prepare for our business plan, we will see far better results out of it. I'll now pass back to Robin.
Okay, thank you very much, Jamie, and thanks for going through those case studies really that we've been working on and been really close to over the last few months. I think there's an interesting question from Joe, which I'm sure we'll come back to about Staunton Street. Now, I mean, just really as a quick summary, what we talk about this arboricity thing. I hope people have come across it. It's a new product for us, and really just to clarify what it is and why it makes such an impact. It's taking on board real-time data, flow, pressure, transient, and noise. So it's able to use all of those characteristics. It's yielding real-time network models, and some of the key points here are that it's calibrated and automatically updated. So as Jamie said, we're not relying on 5-year-old models that have been created that are almost out of date the next day. It's taking live data and using it in a much more sophisticated way than has been possible before. And what does that give you? It gives you full network insight, and we deliver this as a service offering, and we look forward to working with others in deploying these solutions across the challenges that each of you face. We've just shown some examples today. So really, thank you from Jamie and I for listening, and we're hoping there's going to be a bunch of questions because it's an interesting subject, and we're passionate about talking about it. So thank you very much.
Thank you, Robin and Jamie. And it is a fascinating subject. And the first question from Joe Parker. What was the cause
Joe,
of the fluctuation?
I could probably spend a whole presentation on just this alone. But in the interest of time, I'll very quickly say that there's a mixture of pumps at the large blocks of flats, a number of shut valves after mains renewals that have been done and put back correctly, a number of valves that have been shut for a long time that were unknown to be shut. In Portsmouth, we have lots of valves, and that means that they're open when a right-hand valve is normally shut, and so it causes a lot of confusion on the network. There is also, as well as that, a separate large user in the area as well that was causing a lot of confusion, and we believe to be the main reason for the transients, but was actually completely fine and was not causing any issues at all. So it's a very complicated network right in the middle of a city. And our network's very widespread. It's not like a DMAs that are very close, and so therefore in this area there was tons and tons of things it could have been very close to each other, and lots of blocks of flats. Not quite London level, but lots of blocks of flats, and trying to determine which one it was very, very difficult without Robin's help.
Great, thank you. And we have a question from Gertz Chana. What physical changes did you make to the network to reduce
was to open up the network and to rezone it in order to take the part of the network that was where the transients were and put it onto a larger pipe network, and so it was fed in from a different direction in order to minimize the amount of the effect the transit was having on the rest of the network. So as we kind of zoned in these block of flats and moved them away from where the pressure fluctuations were happening elsewhere, the customers complaining, and took it straight to the trunk network, really. And so in that case, that's what we did. In other areas, there are separate things that we've done, such as, and obviously always talking to the maintenance people of these flats to try and improve and reduce these transients across the network through more capital intensive solutions.
Okay, we've got a couple more. Distribution across the whole of the UK. Is that one for Robin?
Maybe? I just froze there, but
froze for me too.
Yeah. And Robin, do you want to go? Just
yeah, sure, absolutely. I think we all suffer from I don't know digital twin confusion in some respects, because what is a digital twin? I mean, the simple realization that we talked about with Portsmouth Water is really having a mirror of the network, so even a technician actually at an asset doing a job can actually understand how the systems work. Now the question is obviously how close are we to having that? With the wealth of data we've got, and focusing on outcomes rather than data lakes that I feel we can drown in. It's using the right information. So having pressure data, having pressure head, having flow data, having noise data alongside this, bringing those elements together. And what we've done with Arborist, but also working with the modeling packages. So working with Innovyze, for example, to understand what models exist already and to augment those, to make them live, is now a reality. And it's only recently, because of understanding the algorithms that are required. I mean, there's some basics in there, but you need to put them together in the right way, combine all those attributes together properly. And what we've been able to demonstrate is that you really can understand the network, and even the simple cases where the Portsmouth Water team were convinced that the valve had been opened. We ran the models, that just can't be true. So by a simple process, we could deduce what was going on and then resolve a problem that had been kicking around for ages. So it is possible now to do this, and this is what we are doing with Portsmouth.
Great, thank you. And a question from Chris Rees. A very interesting presentation, both. Great to see a mix of sensor types used. What is the average number of sensors you need per DMA to allow the model to run effectively?
So it's interesting with the Portsmouth area because there are large zones tend to be different to many of the other UK utilities where DMAs are a particular size, sort of varied, but much bigger in Portsmouth. Now we've always said across a typical DMA that around 4 or 5 devices are required. What we do with Arborist, and this is part of the service model, we start off with a higher density and then we back away if we need to. So we support and service the application. So we're not asking customers to buy the devices. So it becomes a slightly different proposition that it isn't buying an asset, deploying it, letting it get out into disrepair. We can go in, deploy the devices as appropriate, and it could be the inlets, key assets, outlets from the system, PRVs, pumps, and so on and so forth. So we can design a deployment scheme, understand the network, and then back away. If it's particularly calm, we can back away. So, but typically 4 or 5 devices per DMA is a good number. And applying that can be an expensive proposition across many zones, and perhaps focusing down on the critical areas initially to prove the value of the analysis and the model, but of that order. Hopefully that answers the question.
Okay, thank you, Robin. One question from an earlier discussion I have here. What makes your CPIS score unique? And how is it different from just measuring the magnitude of the transient?
What we do with CPIS, we developed an algorithm that understands the pressure fluctuations. Well, we have the benefit of 128 samples per second, so we can see those variations. And what we do, we actually compute it on the device. So the device itself is listening out for the variations in pressure, and it's accumulating those into this metric. What it can then do is it can alert anomalous behavior in the trend. Now, what it was able to do in Staunton Street, for example, was to identify really quite a horrific level of pressure volatility, dynamic pressure changes in the network, which were ultimately very damaging. And the scale they were at was literally almost literally off the scale. And using that metric, we were able to understand the improvements that were made with the rezoning and the work that Jamie talked about. And actually the journey continues, because if you look at Staunton Street, ignore the first part of the scale, it's still quite high. So the impact of pumping schemes locally in the flats, but also potentially other aspects of the network. This metric allows, by really understanding how pressure is working, not just the magnitude, but the variability, That's what gives its unique benefit, and that's what gives unique insight and the ability to deal with those issues and turn them into outcomes.
That's great. I think that's all the questions we have for you for now. So thank you very much. But again, people can speak to you later in the sessions outside. So thank you both, Jenny and Robin. Okay. Now we're going to move on to the next presentation, which focuses on, again, digital twinning and the development of a DMA real-time pipeline hydraulic simulator. So I'm going to welcome Glyn Adicott, Operations Director, Hydraulic Analysis Group Limited, David Gable, Project Delivery Manager, Thames Water, and Sarah Vananther, Project Manager, Morrison Utility Services. So the twin incorporates PRVs, DM flows, smart meter data, and GPRS pressure loggers. The twin is also driven by transient pressure data to reduce new leakage by identifying the source and cause of the transients, so remedial measures can be implemented. The twin was used to reconfigure the DMA and to reduce existing leakage by incorporating acoustic logger data into the twin. So I haven't, hopefully I haven't just stolen your thunder there, but I'll hand over to you now to tell us a little bit more.
The digital twin trial that we run in Thames Water in an area in South London. So our digital twin is a simulated copy of our network. It shows the water going in, how it moves, how the network pressures are changed, and how using the pressures can simulate or assess if something isn't quite right. The engine calculates, and Glyn will talk about this a bit later on, but the engine calculates the pressure it should see and then highlights if it doesn't see it. So if there's delta, and then works backwards to establish why that isn't why. So it could be leakage, could be demand, it could be a whole raft of reasons, and we'll talk about a few of those later as well. It could be absolutely anything on those. In our customer programs team at Thames, we've installed over 500,000 smart meters, and we're installing another 400,000 in the next AMP. We've got a number of pressure loggers across the network as well, but as part of this trial, we installed a number of new NB-IoT loggers. It uses our fleet of acoustic loggers, so we've currently got 26,000 acoustic sound loggers deployed. And it also looks at things like temperature and any other inputs we like. So our SCADA data, for example, from our water treatment works, our pressure data from our PRVs, it incorporates every single sensor that we've already got. And that's the key bit for our model, is that it uses all the data that we've got already. Apart from a small number of added pressure loggers, everything else is data that we've already captured. So we're not installing millions of pounds of new assets or millions of pounds of anything. It uses what we've got already, and that's one of the key benefits for us. It's a smart digital twin without spending the smart digital twin money that we've heard so much about. And our trial was in a DMA in South London called Oxley's Wood. Now it's a part of London near Deptford, in Lewisham/Deptford, and it's very hilly. As you can see on the map, it doesn't really do it justice, but there's quite some high points there. You've got Telegraph Hill, and you've got the Greenwich Observatory just on the outside of it as well. So it's quite a hilly part of London. Very high pressures, very low areas. So it's very topographic and right for pressure management. And the twin utilises the data coupled with the existing data sets. So we had a lot of high leakage reoccurrence in here, and we'll talk a bit about that later as well. A lot of high pressures and a lot of pressure transients that people had always anecdotally blamed leakage on, but didn't really know where they were coming from or why it was until we started doing our digital trial. And within days of starting the trial, we found our first issue, our very first transient pressure wave going through the DMA. And Sir Ruben will talk a bit about that as well. Sir Ruben?
Thank you, David. So good afternoon, everyone. I'm hoping you're enjoying today's session. It's quite nice to hear all the lovely presentations going ahead. So I'm just going to briefly outline how we built the digital twin. So it starts off with basically incorporating our GIS shapefiles from Thames Water and importing it into our software Verisim. And what we had to do is to go through a process of correcting a lot of errors within the shapefile. So there's a lot of floating pipes which need to be hydraulically connected so that the DMA actually works hydraulically. Now, one of the big things about the digital twin, which we've created, is it's mainly powered through our smart meter data. So this DMA is covered with about 25% of smart metering data, or 25% of the customers within this DMA have smart meters. And we not only incorporated those meters into the digital twin, but we also have what we call bulk meters, which are high density property meters, along with our district meter flow meters, all incorporated into one place. This DMA is also pressure managed, so it has 3 inputs flowing into the DMA, and each of those inputs have a PRV. So we're able to actually incorporate the functionality of the PRVs within the digital twin to sort of model the control functions and see how the control affects the DMA. And then what we did here, which you can see in the green dots on the screen with the black squares around it, we also installed about 8 pressure loggers strategically around the DMAs to really look for pressure deltas, which my colleague Lynn will come on to next, to pick up potential areas of leakage, but also things like shut valves and other anomalies which could be causing problems within this DMA. So over to you, Glenn.
Okay, thank you, Sir Ruben. So first of all, basically our twin, it's a very powerful tool. So first of all, we'll talk about the actual model. So there's been lots of talk about software models, hydraulic models. The difference between VeriSim and other packages on the market is they're steady state models. They'll capture a snapshot of data and try and evaluate with this. Ours is a transient simulator, so a surge analysis model. And HAL, or Hydraulic Analysis Limited, we work for all the UK water companies on surge analysis. We have done for 50 years, so we have models all over the UK. But it's effectively a filter. So we throw as much data as you can give into the twin, and it will deal with it, it will handle it. And it basically then compares what should be happening to what's actually happening, and we can produce some fantastic visuals as well. So first of all, one on the left, which stands out, that's basically a heat map of demand. So this will be running live. This runs live in the Thames Data Factory, and it will show you how your demand changes, in this case, over a 24-hour period. The darker the area, the higher the demand. So straight away, it gives you an idea of how your DMA actually operates, and that in itself is really valuable information. The top right screen is, as Ruben mentioned, there's 3 sources into this DMA through 3 separate PRVs, and you can see that the colour represents the source of water, the dark blue, the green, and then on the right hand side the pink. Now interestingly, if you look on the right hand side, you'll see the pink disappears because that PRV shuts at night to allow the other 2 valves to control in a stable manner. So you can actually see where your water comes from and where it goes and mixes within your DMA. And you might have very different water quality and water sources that can explain why the taste of water might change over a period if that was the case. But by far and away, the most powerful part of it is what we call, as David mentioned, the pressure delta. So basically, you input all this data into the twin, and then where the twin doesn't match reality, it flags this issue up. And that could be a blockage, it could be a closed valve, it could be a leakage, it could be anomalies, it could be errors in the build of the data. So basically, it allows you to actually then understand and rectify problems in the network. So next slide, if you can, David. Okay, so how we actually build the twins? Well, first of all, the most important part of this, which is just fantastic, is the actual smart meter data. So Thames have a huge deployment of smart meters, and that provides such valuable information because one of the weak spots of any twin is the customer demand. So, for example, we've had a long-established twin of the whole water supply network of Dubai, but that's driven by billing data, it's estimated data. But what we're able to put into this twin is actual known data. So we actually input our smart data, and in order to avoid modeling every house, we'll effectively group together properties onto nodes within the twin, and that may include smart data and non-smart data. So we amalgamate them into points using something called the Thiessen polygon technique, which I'd never heard of a few years ago. And then the flow data is aggregated at nodal points. So basically we have the flow coming off at various points in the twin. And then, similar to past presentations, what we do then is we compare the model values to actual values. So where you have a leak or a burst breaking out, you will have a change in pressure, and then using the algorithms in the twin and the simulator, we're able to locate the burst and leak. Now, unlike a lot of other products on there, because ours is a transient simulator, we actually model the pressures traveling through the system, the pressure waves. So as a burst occurs, it will travel through the system. We will actually model and propagate that, and that allows us to actually then find and locate the burst by the actual volume of data we process. So, for example, in this twin, we are carrying out thousands of calculations a second. Believe it or not, our twin of the whole of Dubai, it actually has a million pieces of data pass through our twin every minute. So just huge volumes of data, and that's not even including transient pressure data. So you can throw a lot of data at the twin, and then it will show you the output. Okay, the next slide if you can, David. And probably one of the most interesting developments, and we think this is one of the unique functions of our software, is we picked up a number of pressure transients which were entering our DMA from the wider supply system. So if you look at the picture on the left, what our simulator does, it actually models how that pressure transient travels into the DMA and where it goes to. So we might only pick up a transient at one point, but we can actually show how that travels, and you can through the system, and you can look at any one point in your DMA, and you can see what the pressure transient is. Now, the darker the color is the bigger the pressure difference. In this case, it's the pressure difference of the transient that causes the damage to the pipework, and you can actually model it. So we don't need a huge density of high-speed sensors. We only need a few, and we can show them exactly how that transient passes through the system. And we know this is a unique function of our software, and that ability to actually model and track the transient. In this case, you can then we know the source of the transient, we know what causes it from the supply system, and we're now taking steps to rectify that. Okay, so over to you, Sir Ruben.
Thank you, Glenn. Next slide, please, David. Okay, great. So as you can see, the graphic there is quite revealing in terms of the path of the pressure transient. So what we decided to do is we decided to check whether the path of the transient was actually causing significant damage. So what you see on this slide here is a plot of all the leaks within this DMA, spatially plotted over the last 3 years. And when you look at it, there isn't actually anything particularly significant coming out at you. But when we ordered them in terms of the largest leaks found over the last 3 years, the largest leaks were actually found directly in the path of that pressure transient wave. So what we began to then immediately see here is there is a direct link between the pressure transient wave coming into this DMA and the largest burst found within the actual DMA itself. So it actually tells, or the digital twin in this scenario here can actually tell you where the leaks are most likely to occur, because we've got to the root cause of the leakage within this DMA. Over to you, Glenn.
Okay, thanks. So I think it's jumped to one too many.
Jumped the slide.
No.
Is it coming back? Okay, so I'll talk to you guys. So we're talking next about remodeling. So one of the issues we found was we found a problem, and what can we do to rectify it? So the issue with this DMA, as David mentioned, is it's quite hilly. So first of all, one thing our twin can do is actually try and visualize the DMA and visualize how the elevations change. I think it's gone forward again one too many, David. I'm still getting the.
No, it's not. This is the next one, Glenn.
Oh, is it? Right. Okay. Yeah. Okay. Carry on. Anyhow, so basically we've remodeled the DMA, and we've realised that there's certain things we can do. So first of all, we can actually change the way the DMA operates. So you can actually create a sub DMA within this DMA. So we've actually halved the pressures in some of the areas by actually closing around 10 valves in the DMA and dropping the operating pressures. So we now have half the DMA supplied from 1 PRV and the other half by 2 PRVs. Straight away, that's half the operating pressures. So more importantly, as well as reducing the leakage or the background leakage, it actually also allows us to minimise the damage that the pressure transients caused. And the great advantage of the twin is that we can actually use that to actually see what will happen. You can test out ideas and solutions. So rather than going out in the field and thinking, well, what will happen if I try and do this? You can test out solutions. You can optioneer it. You can do whatever you want and test out without actually breaking the real system. And that's our real strength, is then the solution. So it's about not just about find and fix leaks. It's about finding out what's causing the leaks, in this case, the pressure transients, solving, eliminating the root cause of the problem, but actually then also reconfiguring the DMA so to reduce leakage in the long term. And then after that, we can then focus on other areas. I'll hand over to you now, Sir Ruben, for the acoustic bit.
Thank you. David, I think this is my slide, so okay. No need to move it forward.
All right.
Okay, brilliant. So one of the powers of the digital twin, I've heard a lot over the course of today about integrating data and having it all into one place. So you see a couple of examples of anomalies which we've spotted through the data sets and via the twin, which normally wouldn't have been spotted. So on the graph on the left-hand side is a user which is drawing about 2 liters a second out of this network. Now it's buried in one of the metadata, and when we came across it, it actually flagged that this user probably has an incorrect or giving us an incorrect demand allocation, thereby possibly being incorrectly assessed as leakage within the DMA. And it's possible to actually draw these kind of anomalies into the twin, so the twin can actually identify these patterns and bring them to the forefront. The next two graphs you see there are actually taken from our acoustic loggers, which are provided by Halma Water. So David mentions we've got 26,000 of these devices across about over 300 DMAs within Thames, and this DMA alone has probably about 400 loggers. So the aspiration, and we're currently working on this now, is to integrate points of interest through auto-correlating acoustic loggers, and we've done trials with both Halma and Guterman, and pulling that together with our pressure data anomalies. So you kind of get the validation of the points of interest before you dispatch leakage teams. Now, the aspiration from here is, like you can see on the far right-hand side, where you've got a usage heat map, is to potentially create a leakage heat map of the DMA and toggle between the two. So you can see then direct relationships between what our smart meters are telling us and what our leakage devices are also telling us, to get a full picture of what's going on within this DMA. Thank you. Next slide.
Okay, so I'd like to talk about tangibles. It's okay, it's already got talking about some sort of pilot we had, but what's it actually delivered? What does it actually do? Well, first of all, I think one of the best benefits of this is we return clean and accurate GIS data back to Thames, so they know then that the asset data they've got is correct. And also it gives a live pressure, the pressures and flow, live picture of pressure and flows throughout the DMA. And that itself is an easy statement to make, but our twin isn't something that you just sits offline and every now and again you put some data through it. It runs live and it's designed to run continuously. And the hardest thing with designing a real-time simulator is actually having it continually running and dealing with data and bad data and having filters in to handle bad data so you don't get the garbage in, garbage out. So our strength of our simulator at the start is our ability to ensure that we're only driving it with data. And this technology for real time comes from the oil and gas industry. So these simulators have been in use in oil and gas assets all over the world. In fact, most oil and gas lines coming into the UK have our twin sat on it for network management and leak detection. So you get this live picture. At any one point, you can look at the pressure in any pipes, you can look at the velocity in any pipes, the flow rate in any pipes, and you can see how that changes over the day. We, as I mentioned, identified and tracked a damaging pressure transient entering the DMA from a control valve at Deptford, which we're now taking steps to mitigate. We identified a zonal valve that was passing, causing a breach. Again, that just created the error between the twin and reality, flagged a problem in this area, and investigations found the breach. We've identified a number of leaks and usage anomalies, which add up to over 1 megalitre per day. So we've already targeted 1 MLD in this DMA. And also we've developed the solution, as I mentioned, to reduce unaccounted for water by a further MLD by closing 10 valve and optimizing the PRVs so we can halve the pressures in the low elevation, high leakage areas of the system. But more importantly now, we're also actually taking steps with supply interruption to actually model critical valves. So what we can do is identify that for a typical DMA, you might find that only 15% of the valves are critical to prevent SI events. And we are now with Thames Water rolling this out onto other DMAs to actually ensure that the maintenance program of valves only needs to target your critical valves. So any SI events will only affect a very low number of customers. And I think one thing we haven't mentioned as well is actually behind all this, we also carried out some blind leak tests. So Shrewben's team at Morrison's undisclosed time to us actually cracked open a fire hydrant in the DMA and waited to see if the twin spotted it, and we got within the same street. So we've already independently tested this. So it's the ability for it to react to detect anomalies. But certainly from our point of view, the number of closed valves were found as being highly significant, which we're now taking steps to open to improve the hydraulics of the DMA. So it's the strength. It gives you a complete picture of everything within the DMA. So it's back over to you, Ruben.
Thanks, Glenn. It's the next slide. So yes, as Glenn mentioned, we had a lot of fun with that little experiment where I had to test Glenn's digital twin, or our digital twin, I should say, to see whether he could actually pick up those hydrant flushes, which he did do successfully. So pretty amazing. So what are we doing in the future, or what else can we do with the digital twin? So what you can see on your left-hand side is if we had this DMA from scratch and we're doing conventional leak detection, we'd go through a process of what we like to term high-definition step testing, which is to step down this DMA into small chunks and find leaks and compare them with what consumption is going through that actual DMA. The hope in the future is actually we can do away with that kind of technique. So we won't have the sort of violent interaction which may be caused through step testing, and actually find leaks through pressure drops or pressure deltas, and actually follow the water around to the leaks. So you can't see it quite clearly on that graphic there, but what the digital twin is modeling is actually the direction of water through all our pipes. Now, if you know what the expected pressures are on each of the and every one of those pipes, and you can sample the flow of water going through the pipes, you can then begin to see where leaks could be. And in theory, you could join the dots and actually eventually find your big to medium-sized leakage. The other element, obviously, is to bring through all our data sets into one area. So what we're trying to do is to also see whether we can measure the size of the leaks, so you can prioritize the leaks in terms of size, and also the time it occurs by looking at your nightline increases or your pressure deltas, all at a particular moment in time to see where the significant events occur. And also another very good innovation we've done recently, which has been modeled through the digital twin, is to check all our critical valves within the DMA. So if we're trying to mitigate supply interruptions, we can actually go through the DMA and say, rather than checking 100% of all the valves within the DMA, we only have to check now on average at the moment 20% of the valves to minimize significant supply interruptions and reduce the time of that actual interruption is, because the valves have already been pre-checked. Thank you. Next slide.
So the last couple of slides from me, just to round it off before we start taking questions. So I'm going to just highlight how much the digital twin utilizes all our existing data with a couple of extra loggers. So it pulls in the data from our massive estate of smart meters, GIS, SCADA, network assets, so our pressure management, our district meters, zonal meters, all the other telemetry that all the water companies have got spread across their networks. It just uses all that data and pulls it into a single hydraulic model and then geographically represents it. And the end users of that could be anyone from your system engineers or your leakage engineers to your demand planning, to your asset investment, network modeling, if you've got an incident, how you respond to that, your capital delivery investment requirements, technicians on the ground being able to see what's going to happen when they shut the valve, or if they need to rezone and take those decisions in the field without having to kind of second guess themselves. And then developer services for modeling new demand. So what Glenn didn't allude to is you can also put extra demand on a pipe to see what will happen to the pressures. So if you want to say in London, we want to build a big tower block, for example, you can simulate the flows and see what that does to the pressure, and then work out if you need any network reinforcement or whether there's sufficient demand. So the digital twin does a whole lot more than just leakage. It looks at the whole DMA health, as it were, and allows you to target your investment and your needs effectively. And the kind of the future within digital twin within Thames Water is, so we want the aspiration is we roll it so we've got a library of off-the-shelf digital twins, live off the shelf. So you can, if you've got an incident or you want to run something, you just go to that shelf, you pull it off, and you can work with it. We connect the digital twin to our data factory. So we've got a massive data factory, a data lake, and you'll hear that all the time, of all our data and a single source. So we just build an API pipeline into that lake, and the model then runs off that lake effectively. And we can model the what if scenario. So like I just said about developer services, we can simulate the demand, or we can, if we're doing capital investment or rezoning or anything like that, we can model that impact and model the impact to our customers. And we can target our efficient investment. So we can work out where we best spend our money, not just whole scale DMA replacement as we used to do, but we actually do the targeted bit that we need to do, rather than playing it safe and doing everything. You can target your investment. And we go to the root cause of leakage. So as Glenn spoke about, we found the root cause in this DMA happened to be a pressure transients coming from a treatment works, from a valve that not many people knew about that used to open up when the pumps tripped. So now we know that, we can now fix that and stop that leakage. So the payoff is we'll have reduced leakage, and we'll see the payoff of that in a few years when we stop getting those big pressure transient leakage, and ultimately improve our service to our customers by being in control of the network, by knowing what's happening, by seeing things before they become an issue. So we'll be able to see that burst developing before it blows up, before the customers get no water, before anyone else highlights that issue to us. We will have a planned, controlled method to deal with that burst, and that's ultimately improving our SI score and our service to our customers. And that's it. Thank you very much. So,
well, thank you very much, David, Glyn, and Soroban. That's, again, fascinating presentation. We have a few questions here on the side. I have a similar question as for Portsmouth Informatics. Will you be rolling this out across? You've just answered that one, yes. And do you think this will be the norm for managing networks in the future?
I can't answer that. Ultimately, I've seen so much benefit from rolling this out just in one DMA. And whenever I brief anyone in Thames Water, so I briefed it to the exec on Friday, and they said to me they want me to roll it out across the whole of the business. So it's very much in its infant stages at the moment. But I think my own gut feel is it will lead to massive service improvements and visibility when you know what's happening across your network and make early interventions. So yeah, I can see that being the future.
This will be the future. Okay. From Mikael Wilmot, again, another cracking presentation. What effort did it take to initially cleanse or validate the data? Soroban mentioned having to sort out floating pipes. Did most of the initial validation require field surveys?
So initially, it sounds a big exercise, but no, the vast majority of it was just actually something that we did in the office, and I have a team of 40 hydraulic engineers, and all they do day in, day out is build and manipulate and calibrate models. So most of the work was just it was quite obvious. There was one or two questions we have, and that's when it was great with this collaboration, because I could just turn to Ruben and say, can you go and have a look at this valve? We think it's closed, and he's deployed a site team, and sure enough, we'd find out that it was closed. So I'd say probably 95% was done from the office, and then the 5%, the difficult bit, we then just pass over to Morrison, and they get back to us with that.
And the brilliant thing I'd just like to add to that as well is Glyn has directed our teams pretty much, or Glyn's team, or should I say the digital twin has directed our teams on site. So we did find when we looked at stuff hydraulically, we did find pipes which we thought were not tied in, actually tied in at either ends of the streets, and we actually have currently found about 5 or 6 shut valves, causing significant circulation issues within the DMA, which are in the process of getting opened up. So that's all come from actually the pressure anomalies we're spotting within the DMA itself not making sense. Very often they could be misconstrued as leakage, but they also do highlight severe hydraulic issues like shut valves within the DMA as well. So that is an added benefit there.
Great, thank you. Chris Rees asks, thanks for the presentation all. Is the plan to roll this out to all DMAs as an anomaly detection system, or is it to be targeted at those with specific issues?
In our initial trial, when I briefed this to the exec last week, their indications were they want me to roll it out to the top 20 leakiest DMAs as a leak detection tool, and then across the business, across all DMAs. But it's all subsequent, all depends on the success of the trial. But the aspiration is we roll it across as an anomaly detection tool, an early warning type tool as well.
Great. And last question we have here, Paul Taylor. Do you need to have real-time customer meter data? Will the model give effective results?
Should I take that one? So yeah, it's a good question. At the moment, Thames are on a mass deployment, but not every property has a smart meter. So the advantage of this is where it's unmetered. We've actually found that if we take the smart meter data and take an average of all the smart metered properties and apply that to unmetered properties, you actually get a really good match with the twin. So our plan is not to actually drive it with continual smart meter data, but we would have a periodic refresh, maybe once a week. You get a new batch of smart meter data to account for seasonal changes, and then update it that way. So yeah, the model still works very, very effectively if we don't have smart meter data. The fact that we do have customer data, though, it's fantastic. I mean, it really is. And it all credit to Thames. As soon as they identified the amount of data they had available that was sat there relatively unused, and they were straight away on board with this to actually find a way to bring it all together actually find a way to actually, you know, take all this data and then view it very, very simplistically. And for that, they obviously spoke to ourselves. And as I said, this tool we've got is, whilst it's new to this level of use in the UK, it's proven worldwide. And for example, we are embarking on a twin of the whole of Qatar next. So we just received a contract to build one model of the whole of the country. Every single pipe in Qatar will now be driven into our twin. So we are at the cutting edge of this technology. And Thames have straight away, because of our history with Thames, and we've worked with Thames for, as I said, 50 years, that, you know, they were very keen to actually bring this into their asset base, realizing that it will just give a very clear and understandable picture of the performance of their assets. So then they can do the difficult bits, as far as I'm concerned, which is actually sorting out the problems.
Okay, and I think probably the last question we have time for today, and I think this is one for you, David. You've indicated in your presentation that to roll out this digital twin, you had a lot of data already available to you, so it didn't require as much investment as potentially people think it needs. However, has this required significant capital investment?
The trial has been relatively low cost, so we're trying to keep the cost to a minimum. The only additional cost we've had to buy some NB-IoT pressure loggers, which we've only bought a handful of those just to supplement the network for a part of the loggers, but we didn't require any capital investment as part of this trial, no.
Excellent. All right, very good. Thank you very much, gentlemen. David, Glyn, and Sarabhan, thank you. So, and now I'm going to introduce the next presentation, which is actually the last presentation for this afternoon. I'm going to welcome Stuart Maudit, MD, SME Water, and Adam Perkins, Leakage Operations Lead, Severn Trent Water. This presentation takes a different approach to modelling, and this time focusing on dynamic pressure modelling. And we're going to provide, this team are going to provide insights into how dynamic pressure modelling analyses data from a fixed monitoring network of over 6,000 pressure flow monitoring sites across 500 DMAs and delivers a real-time response to network changes, enabling Severn Trent to quickly localise larger bursts and prioritise smaller events. It has also proven an effective alternative to fixed acoustic logging for both plastic and more rural networks. Okay, over to you, Stuart and Adam, please. Right.
Brilliant. So I'm just going to start off by talking about some of the Severn Trent programme over the last couple of years. So this started back in 2018. But before going to the technology and still going into some more of the detail, we're going to talk about some of the people journey that Severn Trent have been on over the last couple of years and how that's going to help enable the maximising some of this technology. So I'll just move on to talk about some of the Severn Trent challenges and why we changed. So just to give you a bit of background of the Severn Trent challenges, we obviously had the immediate AMP7 challenges. So just to put into context, our AMP6 challenge was around 6% leakage reduction, and we had the 15% target for AMP7. So really this was a shift in terms of the need and the size of the challenge, 60 MLD in Severn Trent terms that we were looking to save. We also, at the same time, for our PR19 plan, our water resource management plan, had some severe supply and demand deficits approaching in the next couple of AMPs. This was predominantly focused around North Staffordshire, Nottinghamshire, which by coincidence was some of our best performing leakage areas. So it just gave us that extra challenge to push leakage lower in some of our highest performing areas to achieve not only the leakage target, but also achieve some of our water scarcity challenges as well. We had about 150 MLD target across the AMP to reduce to meet some of them challenges. Now, not all of that will be through leakage, some of that's through metering as well, but we knew we had one hell of a challenge on our hands. And that for us really needed a complete shift in our strategy. So we were talking about these sort of things back in 2018. We were reviewing our operating model for people. We were testing small scale trials, but the 15% challenge really just motivated us to increase that. And our PR19 submission also needed some answers on how we were going to address some of these big challenges. So this kind of caught that perfect storm for us to look at all aspects of our leakage model. And we're just going to walk through some of our people and technology around how we've embarked and facing some of them challenges. So next slide, please. So the Severn Trent approach. So back in 2018 for AMP6, we had a predominantly outsourced leakage operating model where we had around 75% of our resource was externally sourced. We had a small internal resource, but they also delivered multiple measures. So they weren't solely dedicated to leakage. They were also supporting out of hours cover and supply interruptions. So we didn't have an internal dedicated resource, and we had a large third-party resource delivering our leakage target. We looked to do this completely differently. We did a small-scale trial in one of our areas in Shropshire, and we looked to bring in not necessarily more people, because the model was actually that we moved to was actually less people, but a higher caliber, a higher skilled resource, and starting to really take that core competency back in-house. So we drove a big internal recruitment drive. We recruited 115 new roles into the business, what we called water network technicians. And we led this through an ownership and a local accountability model. So each one of our new employees would own 30 to 35, probably to 45 DMAs each. And they'd be solely accountable for the leakage in their areas. So they weren't just looking at how many leaks do I need to find this week because the model tells me to do this. It was purely looking at what needs to be true for me to reduce leakage sustainably over the long term, and how can I really understand my DMAs better than anyone else. And that helped push that ownership and accountability right to the front line of the organisation. So with these new roles, it was really clear when we went through that recruitment drive, we wanted people who were going to challenge the status quo, we're going to really adapt new technology. And, you know, this led to is kind of hiring on a behaviours and strengths model more than an experience model. We knew we had a couple of years to get ready for AMP7. And this allowed us to, so for our recruitment drive, we did bring in around 30% of our staff completely new to industry. So this is people that have never picked up a listening stick in their life. And we knew that we could train people to a certain standard over the next 18 months to get ready for them sort of challenges. We also knew that some of these people would be more kind of adventurous in terms of taking on new technology and maximising to their full potential. And this is what we've seen. We've seen people kind of overtake some of the longer term pros quite quickly just by having that curiosity to embed some of these technologies. What also we found is that we've got an example there on the right. We create personal performance dashboards for each of our technicians. This is Luke in Leicestershire. He looks after an area that you can see. And some of the lines on that top left chart is really just his historic trend lines. And you'll see the purple line, which is the last year's line where he achieved the historic best for the area. And again, up until last week, was on course for another fantastic year, other than the cold weather snap that we've seen. He's in complete control of his operability, his leakage, and also he gets to really think about how he's going to reduce leakage over the long term. So we've heard a lot about how to reduce burst for the future, and so that he's not kind of busy year after year after year, because that will kind of run its course and will run out of benefits. He needs to also think about pressure management opportunities. And to do that, we need to give him some extra capacity. And that's through some of the solutions that we've looked at over the last couple of years. So just moving on to the next slide and the actual, some of the kind of theory that we had at the start of the program. So we'll introduce DPM at this stage, or dynamic pressure modelling, but really it focuses on, if you look at the left-hand chart there, the traditional method of ALC or leakage detection is this kind of economic model that's built on letting leakage get up to a certain level and then it becoming kind of leaky enough to send someone in. And we kind of wanted to just bust that model completely, because we knew that that wasn't going to drive a 15% reduction over the long term and was just keeping kind of a lid on leakage, really. We knew that we had to move to a different model where we would embark into DMAs more frequently for less leakage that was available, apparently, but then bringing it down more often. So this little and often approach instead of this kind of let leakage get up to a certain point and then start to invest time and effort. And we knew that if we looked at all of our DMAs, about 3,300 of them at Severn Trent, we knew that if we managed to kind of create all of our DMAs at the lowest achieved level all at the same time, we would have dropped leakage by 150 megalitres. So we knew it was possible. The ADOC challenge of leakage is how to keep it there. And that's where we started to look for the technology to help us do that. And that brings on to the right-hand side of the chart. So we knew that acoustic was a proven technology, and we knew that most industry were moving to fixed permanent acoustic loggers, and so did we. We've got a substantial amount of them, but they are perfect for certain environments. And on there, we've got a scatter graph of all our 3,300 DMAs by kind of urban to rural and metallic to non-metallic assets. We know that urban Metallic are great for acoustics, and that's where we looked to put them. But it left us a big gap in the rest of the network where we were going to have a particular problem. And that's where we looked for DPM to kind of bridge that gap. And although a less proven solution, we knew that over the long term, the more plastic assets are put in the ground, the more kind of leakage reductions that we needed in more rural areas, we needed an alternative solution, another tool in the toolkit. And that's where we looked to employ 5,000 permanent pressure loggers across 400 of our 3,500 DMAs. And so that the rough maths there is that we required about 10 to 12 permanent pressure loggers per DMA to give us this level of insight that we're going to talk about in a bit more detail. So let's move on to the next slide. So I'm just going to talk about kind of what DPM is in layman's terms and how I understand it. And Stu will go into some of the more detail. But just to give you an idea of what the frontline technicians, the water network techs see and get, and this is only a recent, a lot of work's gone into this to get to this point, probably 18 months of installation, development, fine-tuning of the algorithms to get to a point where we can start put this in people's into the front line. So the screenshot on the bottom left is a collector app visualization of what the guys will see now out in the field, and that will start to highlight polygons within the DMA where we believe if there's a burst, where the likelihood is that burst is appeared. So an example there's a 3Q burst in a particular area, and in this particular example, the right-hand chart shows us that it's zoned it down to a much smaller area of the DMA, reducing our time to find, but also meaning that, I guess, from an economic perspective, we want to be able to kind of do that little and often approach where we're going into DMAs, we find the leak quickly, we get back out and move on to the next one. And to do that, obviously, if we want to do that with a limited set of resources, we couldn't really, because we'd be in there surveying the whole DMA looking for one leak. We needed something that's going to help localize, and this does that for us. It also has the added benefit, we believe, is kind of reducing the need for step testing, because these are non-intrusive assets that are giving us smaller zones. So in terms of narrowing down the leakage we're looking for, we're not having to spend days, night hours, and also the disruption to the network that can be caused through step testing. So it's starting to limit that as a potential of opportunity. And I guess moving on to some of the kind of early signals and early benefits that we're starting to see in our DPM DMAs, you can see there that we're starting to really get this out to most of our front end users now. So it's worth saying there's been a lot of work. We're starting to really make this kind of BAU process with the teams for them to use this day in, day out. And we can start to see that now the teams is pulling this into their day-to-day working, we're starting to see that benefit start to land in the actual frontline business. So you can see there that we are achieving around 30% faster leak find in the DPM DMAs compared to the non-DPM DMAs. So the orange line there compared to the blue line. And then moving on to the next slide, it's also helping us find leaks or number of leaks per DMA. And I know we're not in a game of just finding leaks for leaks' sakes, but it's also finding us areas of the DMAs or telling us to search for leaks in areas of the DMAs that potentially wouldn't have looked at in the past. And that's starting to see us drive leak find in them areas up. So there's some of the kind of early indications of some successful metrics coming through after a lot of hard work from Stu and the team. But now we're at this kind of tipping point where we're starting to get this into the business, starting to get the people really using this and pulling to use this on a day-to-day basis. I'm now going to hand over to Stu, who's going to talk about the kind of solution, its other aspects of the solution, what it can bring, and what we're looking to maximize over the next few years. So over to you, Stu.
Cheers, Adam. So looking at one of the advantages that we get from the pressure logging that we've got on the network is that it allows us to look at other parts, so not just the burst leakage. So Adam's talked about the burst leakage and the fast to find approach, which has been really useful. But in terms of other parts of leakage, we also accept that we've got kind of background leakage and ongoing leakage in our DMAs, but also across most of the DMAs that we've been working in, we've got large parts that just aren't leakage. So we've seen quite a few presentations today that have talked about demand anomalies in DMAs, about network configuration anomalies, boundary valves being open. And there's a real challenge there for the industry as we go through trying to hit our leakage reduction targets. Actually, there's a large proportion of our leakage, our reported leakage, which just isn't leakage at all. So if we look at how the DPM solution can impact on all three of those areas. So Adam's talked about burst leakage, and by finding these faster, being able to get the most from the resource that we've got with our localization area hotspots, we can start to reduce that. We've also in Severn Trent, some of the DMAs, we've had loggers out for 2 years, 2.5 years in some cases, and we're starting to see some real insights. So over a longer period of time, over extended data sets, you can see those smaller leaks starting to grow. You can see them develop, and particularly when you look across, say, a month's worth of data, you've got extended data sets that you can start to take out a lot of the noise and really understand what's going. So you can see things growing and then starting to go pop as bursts. Then we've got this big chunk at the bottom. So when we talk about things that aren't leakage, we've got things like network and demand anomalies that just aren't really leakage, that I'm going to talk about a bit more. So these come from a number of different areas. So network anomalies, so things like open boundary valves, closed inline valves, incorrect GIS. So we saw a lot of this on the back of the 2018 hot weather incident. So there are quite a few areas where Severn Trent were forced to open up boundary valves to make sure that customers were getting the supply and the pressure that they needed. And then there was a real challenge after that period to say, well, what should the network look like? How do we know that we've put it back to how it was and our leakage reporting is accurate? So being able to compare pressures before and after gives you that accuracy and that sort of confidence that the network's doing what it should be doing. Similarly, in terms of demand anomalies, we come across a lot of, at one extreme, unknown customers. So people they're just not represented in the system and we're taking water, whether that's illegally from standpipes or otherwise. But more commonly, you've got a known customer, but actually they've got a second connection that you're just not aware of on your GIS because you've mapped what's there. You've also potentially got unlocked connections. So maybe there's 2 connections in there, one's metered, one's not. Or also you've potentially got meter inaccuracies happening on the network. So DPM allows us to start to understand, well, where's the flow going within our areas? Where does it matter? So as an example of this is one of the DMAs in Leicestershire. The analysis generated the area of interest shown there, and we had a burst that was on the continuously logged customer. So actually it was quite a large continuously logged customer, and it was downstream of the meter. What happened in this example was the team went out, did the leakage detection of that area, and came back and said, well, we can't find anything. So we got our team to check the analysis. And said, well, it's definitely in there. We need to go back in and do another sweep. And they went in and identified that it was on that customer downstream of their supply pipe, which isn't somewhere they would normally have looked. So without that confirmation and that extra kind of insight, they would have then gone on to sweep the rest of the DMA or start doing step testing, which obviously is time consuming and starts to impact on customers. So in terms of what this actually looked like on that graph there, you've got the orange, which is the DMA inlet minimum night flow. So you can see there we have a big burst that occurs on the 29th, quite substantial. The customer log data isn't recording correctly. So actually that masks that. So the leakage teams had looked and gone, well, it's not on that customer. That's one of the first things they do. And then proceeded to start looking on the network. When we gave them the confidence to go back in and they then started doing a wider sweep, they identified that the leak was there and got the logger fixed on the customer. So you can see there, that's then clearly where the problem is. The burst that gets fixed on the 26th. And you've then also got a corrected customer log data. So actually that then means the reported leakage going forward is going to be lower because that customer is properly recorded and it's been subtracted properly from the leakage data. So this slide starts to look at historical performance. So Adam's talked about the kind of the 5,000 loggers that were put out. So back sort of from summer 2019, we started working very closely with HydroSave. We've been our fieldwork partner out on this, deploying LX2 loggers from Halma. Prior to this, Severn Trent had done some extensive trials. They didn't just kind of put their finger in the air and decide they were going to throw money at this. We've done quite a lot of trials to make sure it worked and make sure the solution was going to deliver performance. So we had an area in Wolverhampton, which was about 40 DMAs, and we've since rolled out additional ones in that area. And the approach we've taken with Severn Trent is that we do entire control groups. So a control group in Severn Trent is a hydraulic area. So, for example, a group of DMAs all fed from the same pump or fed from the same tank. So here we've got a real block of the network. It's got a variety of DMAs. It's a fairly urban area, but a real kind of mixture of what's going on there. So starting from August 2019, whilst we were rolling out loggers in other areas, we started working closely with the teams to see what we could actually deliver in terms of reported leakage insight and additional information. And you can see there, we kind of had quite a big spike there in terms of lockdown fueled some demand. But the graph is showing the monthly reported leakage in orange compared to the blue, which is the range of historical data, so 2015, 2018. So you see before we started looking into it around August 2019, it was fairly close. And you see you really had a big separation there. So comparing historical performance of that DMA, we're seeing a 25% reduction in reported leakage. And that's a combination of different things in this area. So it's the leakage operating model that Adam's team have put in. It's the reduction in time to find. So we're finding things faster, we're getting them fixed. We haven't got things running for a long period. Also, the teams have got confidence to really go after these leaks. They go and look for something and they just can't find it. The analysis is saying, well, it's definitely there. Let's focus on this. They've got the confidence to push through. And then also, we've seen some real easy wins. There's some real successes in terms of identifying things that just aren't leakage and starting to really drive down those areas of performance. That's it from us. Are there any questions?
Okay, thank you, Stuart and Adam. We do have a couple of questions from Paul Parr. Adam Stewart, DPM seems an ideal solution for burst awareness. In DMAs where you have deployed DPM rather than acoustic technology,
so I can
how have you
pick that up.
tackled reducing existing leakage
levels? So with DPM, we know that it wouldn't necessarily pick up the low-level bursts, incremental bursts. We knew that it was going to help us when we got DMAs low to keep them low. And but what Stu mentioned in the second part of the presentation was probably where we believed some of the lowest achieved levels of leakage were. This has allowed us to push on and actually challenge where we believe the true minimums are. That has helped us push some of these DMAs, not just from water leaking out of pipes, but some of the unusual demand to re-establish where the minimum is. And then I guess DPM is there as a safeguard to keep leakage low and make us aware so that we can do this little often approach. We're not creating loads of demand for the technicians. And really, I guess there's two halves to it, how to keep it low, but also how to kind of breach new minimum historic lows. And it can do both of that. It's just that breaching the minimum historics takes probably a damn sight more effort to get there. But once you're there, the solution will make it quite easy for you to keep it there. That's the approach we're looking at.
Okay, thank you. And we have a question from Jamie Jones. Thanks, Adam Stewart. Adam, did you provide your leakage techs with additional training so that they were able to take ownership of DMAs?
If so, we did provide the guys training. So first, before we knew, because there was a lot of work to get this up and running, we wanted to do some warm-up sessions with the team to expect to give them guys an idea of what was coming down the tracks, because this wasn't an established off-the-shelf solution. So we got them really early involved in what the system's there to do, some of the methodology and the logic for why it's going to give us something different to traditional methods. And then as the solution became kind of more ready to launch, that's when Stu and the team would work more locally. So I'll pass over to Stu at this point to kind of take over from the more recent months and the embedding into the day job.
Yeah, I mean, I think it's been challenging. I think we've seen people who really wanted it and others that haven't wanted it as much, which I think you always see with these things. But as Adam said, I think the guys on the ground, they're really passionate about what they do. They've got this area and it's their patch. They're responsible for it. So they to some extent, some of them have done a really good job and they've got to as low as they really can on their own, working really hard. And they're starting to look around and say, well, how do I go to the next level? Who can help me in what we're doing? So we sort of see that draw from them and the teams. We've been working really hard really with Severn Trent to make sure that we kind of talk about digital twins and all these kind of complex analysis. I think trying to get something that the teams on the front end can understand. They can really kind of say, well, actually, here's a tool that I can pick up and use. And they don't need loads of hydraulics and loads of training and loads of kind of next level analysis to be able to make the use of. They can just pick it up and they can run with it. And yeah, the kind of the draw from the front line has been really great. And you're really starting to see that the more they use it, the more they want to use it, and the more we get great case studies and new people coming in. We've now got a wealth of case studies. So anybody who's sitting on the edge going, well, I'm not sure how this is going to help me, you can say, well, that guy over there, he's got a great case study where he didn't have to do step testing. This one, we had a case study where they dug 3 dry holes, and they were still saying, well, DPM says it's definitely in this corner of the DMA, and on the 4th dig, they found it. They found the leak. So having the guys, it kind of gives them that confidence. The other thing it gives them is, in the early days, we had the odd kind of phantom valve opening and things like that happening. So kind of there's activities, there's night work going on, different teams working on the network, and these guys want to know, well, who's been opening my valves? Why? Who's been messing with my network and causing problems? And the system gives them that. It gives them the ability to say, okay, well, someone opened that valve and it was at 7 o'clock on Friday night, so they can then go and march off and find out who did it, and kind of hold them to account. So yeah, there's a real drive from the teams on the front side.
Yeah, definitely.
So it helps with that sense of ownership that you talked about as well. Yeah. Okay, then I had another question from an earlier conversation. The presentation talked about the importance of Severn Trent's new leakage operating model.
I think
do you
historically
think
we've
DPM would
always
have
driven
worked
people on the
without
number of
this?
leaks found, and that's been the kind of key driver. And that kind of blocked anyone from thinking about taking new technology, because it was like, even if it was going to help me, it was going to take some time to get used to. So we've definitely seen the leakage operating model create that draw. I think it would have been successful, no doubt, and like any other solution, it has to be successful. But when you write the business cases for these big investments, you're hoping you're going to get that extra bit of kind of fairy dust on top, where people are going to take it to the next level and going to challenge these guys. So I know, Stu, when we get like more complex issues, we pass that back to Stu and the team and kind of have a direct conversation with the frontline technician. We don't kind of put management in the middle. We give these guys license to call Stu and the team and say, I'm having this problem. It's not as straightforward as a first thought, and that is going to help, really push SME water as well around what can this solution give us kind of on a day-to-day basis. So we've definitely seen that. I think with anything, if you have really good people, they'll make the most of any technology. And I think we're starting to get, it's worth saying that this is probably starting to become kind of company-wide product and solution for us after 18 months of real hard work. So we are in the early stages, but we're starting to see that kind of take grip in the organization now. So Stu, maybe you want to add something to that?
Yeah, I mean, I think we talked about 2 things there, really. The burst localization, I think as a tool, you can drop that in anywhere and it would work. It would give you some benefit. It would reduce your time to find. I mean, I showed a graph there that showed a 25% reduction in reported leakage in the areas we're working with. The reality is that takes a lot of hard work. The water network technicians in that area, we've got issues that we identified 15 months ago, which are problems with council tower blocks, lots of stakeholders involved, different parties, and the water network techs have, in some cases, it's taken a year of constant stakeholder engagement to work through those issues, to bring those stakeholders on board. You talk to council tower blocks, we've got some great cases where you've got hot water systems, you've got a central hot water tank and boiler system that's feeding 5 or 6 tower blocks across a couple of kilometres, and you speak to the councils about them and they kind of go, well, we've got another dozen of these across the whole of Wolverhampton that we weren't aware of. And those relationships have been huge. So I think without that model really pushing all the time, maintaining action registers, going and knocking on the doors every week and saying, oh, can we do this bit now? Can we get this in? Can we get this meter in? Can we dig that hole? Pushing everything through, really owning those actions and those activities. I think we would have struggled. And I think anybody who's done hydraulic modelling will appreciate that, because in the old days, you'd do hydraulic modelling, you'd have a nice report at the end that said, well, here are the problems with the model, and it'd go on a shelf and nobody ever pick it up. So the refreshing change is that in Severn Trent, you've got somebody picking it up who says, well, actually, yeah, this is my patch now. I don't want to have these anomalies in my patch. I'll bat it out the park and I'll make sure that it keeps moving until it's resolved.
Brilliant. So it's having the data and having the sense of ownership that drives the tenacity, I suppose, to seek a proper resolution. Great. Well, we have one more question here from Richard Kiernan. Are the DMAs the tech's own based on geographical location, or were they assigned to each tech so that each tech had similar levels of leakage to identify.
Yeah, so when we first started this, they are geographical patches, so they are DMAs that are close to each other and connected, because obviously, like Stu said earlier, the interrelationships between DMAs is just as important as the DMA itself if you've got open valves or different things going on in different areas. So they are geographically based, but we've tried to create, I guess, a fair system, because when we performance manage these guys, we want to make sure that they've got a fair deal each. And that is quite hard. We had to come up with quite a complex kind of matrix where we looked at kind of numbers of kilometers of main, age of material, numbers of properties, connection density. You could name so many more that we looked at in terms of burst frequency, how busy are these guys going to be on a week by week basis. And there isn't a perfect science to it. So we've just gone with what we thought originally, and we have tweaked that over time. When new people have joined the business, use it as an excuse to redraw the boundaries on some areas. But we're 2 years in now, and really starting to see that people that have been in their patch, and a lot of the guys often live in their patch. So there's a sense of pride that they come straight out their door into their DMAs. We've seen a massive reduction in travel time. So they're on patch a lot more because they're coming out of their DMAs in their areas. And so that's that. And we know that systems and GIS can get us so far, but we really didn't underestimate the amount of local knowledge that you need from guys really understanding the nuts and bolts, especially over lockdown and stuff like that, when we were there was no history that was going to tell us what was going on during that lockdown. Getting the guys out there and actually seeing it for their own eyes, or seeing which factories were open and which weren't, these are kind of valuable tools that you just can't get into any system. So it may sound like a dark ages approach of patch ownership, but it can be brought into the future with the technology, and you're not going to get these guys holding on to their secrets and taking them to the grave with them. You won't get that. So we've seen the benefits, and it's probably worth saying that in the final year of last stamp, we delivered more than the first 4 years combined in MLD reduction. So we saw the first year of it take hold across the business, and the technology is only going to help these guys take it to lower and lower levels.
Brilliant. Well, thank you very much, Stuart and Adam. That was, again, another brilliant discussion, brilliant presentation, as have all of them been this afternoon. But that brings us to a close for our sessions. I'd like to say a big thank you to everyone who has shared their projects and everyone who's contributed throughout the chat and taken part in the networking today. All of the presentations today will be made available to all delegates, as will all of the recordings, and links will be sent to delegates as soon as they have been processed. So we're looking forward to seeing you again tomorrow at starting time 8:30, with presentations starting at 9:45 a.m. But now is the time to network, visit the expo, and that closes at 6 p.m. today. So again, I'd encourage you all to use the expo and to use the final hour and a bit of the day to do further networking with your colleagues. I think the one sentence I'm going to take out from all of today, which I think was very simple but summarized it all. Robin Bell mentioned that what they were trying to do is take all of our data and put it to its best use. And I think that's in effect what everybody's been talking about this afternoon. And I think absolutely shows fantastic progress and collaboration that is going on within the sector. Have a fantastic evening, everybody, and hopefully see some of you again tomorrow. Take care.